Hello and welcome to Module 1, the History and Value of Systems Engineering. In this section we will talk about the maxims of systems engineering. First of all, what is a maxim? A maxim is defined as a general truth, fundamental principle, or rule of conduct. Another way of saying it is it's a saying of proverbial nature. Essentially, this is a good way to introduce systems engineering because these 7 maxims permeate all throughout all aspects of systems engineering. We'll review each of these in much more detail in the coming slides. First of all, systems engineering focused on the whole. Of all the 7 maxims, this may be the most fundamental, and that's probably why it's the very first one. It is important to understand all aspects and integrations and of all components and interdependencies. That's what systems engineering is all about. While it has its roots in cybernetics and general systems theory, it really does take the concept of holistic view, understanding those relationships and emerging principles, which is a much broader aspect. Viewing as the whole applies to the development environment as well. Subject matter experts within the systems tend to focus on a subset of the overall system. If they're responsible for software, mechanical, or electrical, that's where they see. The old proverbial, if the only tool you have is a hammer, everything starts to look like a nail. They also are very specialized and they know those subcomponents, and that's what their focus in the project is. The reality is they are just one element in the cog of that whole machine, and those elements of software or mechanical or electrical need to integrate in with each other as well as other systems. So the role of the systems engineer is to take the step back and focus on the entire system and truly balance out what those subsets are. Early development life cycles firms focus primarily on product development and production in that order. And what that means is product development focused on product development and then threw it over the wall to manufacturing or production, and then the production completed it exactly as it was designed and then gave it to the end consumer, whether or not it met the original specifications or requirements of the system. Over the years, that obviously became a very short-sighted vision and became much more obvious that needed to change. That came more the cradle-to-grave approach, where instead of taking it just with product development and production, take a step back to requirements development and take it all the way through the lifespan of the process. Now we have what we call lust-to-dust life cycles, which is essentially cradle-to-grave, taking a step even further back. So before, in those bookends, before you even get to development, get into concept of what is the need, where do we even go with the system. At the other end of the bookend, you have the dust. So once it's grave, what do you do with the product? You may have to talk about disposal or recycling. Some products may be just landfill, others may be a system where you have to have information that gets terminated or destroyed or somehow archived. In the past, even the cradle-to-grave concept did not incorporate some of those what usability and the end user has to do with at the end of the system lifespan. This is an example of a life cycle that over the course of a system. And the key components here I want you to understand is, first of all, look at the overlap between the different elements within there, from concept to development to production, utilization, and support. It's not a straight linear path. There is a point where concept has to start development, and then there's a little bit of an overlap. At the same time, you also look and see that there's rework or iteration loops where when a product or service gets further down the line in that system, it has to go and take a step back, potentially to development. This is a clearly simplistic tool, simplistic view of the process here. The reality is there are much more common overlaps, much more variation from overlaps, and rework loops are always present. The further down in that life cycle that you get, once you get into utilization and support, the more difficult, the more expensive, and the more trade-offs that had to be made to take steps back into development. Ideally, you want to find these issues well before they get further down the line, but once you do find them, it's important to go back and stop and cut them off right where they occur so that you can fix them. Once you get into the product utilization support, it becomes even more difficult because once the consumer has the product or the system, now that's a problem where to go and change something becomes much more difficult. Some industries have it easier. Software, for example, will do update patches and changes that they can just do electronically. Automotive might be a little bit more expensive, but possible because they can have people come in and do warranty or service recall types of things. Other ones altogether, for example, if you talk medical industry or medical devices, once a product has gotten out of there, the service is being used, it is very difficult to go back and change it because of the cost or life risk associated with it. As a good systems engineer, you'll need to know where boundaries exist in order to effectively manage against scope. You have to know what is your responsibility in that particular system or what is not your responsibility. Define interfaces up front very early on in the systems process to truly understand where that scope starts and stops. This is especially important if there are multiple concurrent systems in play, which is frequently the case. On the right, you'll see an image that shows both the black box and the white box concept. The black box is a completely closed and has no external interfaces. So all that is there's the inputs, it goes through the system, and then the outputs. The white box model, for example, is when there is an ability to know they have internal and external subsystems that they have to contend with. The reality is the white box model is much more common and is much more complicated to deal with. Systems can oftentimes be organized in a hierarchical manner, and this is very advantageous as a systems engineer if you are able to do so. This allows you to understand all the elements of your system in a very organized and linear light. In this image here, you notice that the system is start off at the very top of the overarching system and then has a subsystem. Then within that subsystem, there are potentially components, subcomponents, all the way down to the part level. You can look at any individual element of that tree and say how the subcomponents integrate in with the system, subsystem components, all the way through and manage themselves within the system. This is also a very positive visual tool to show other people in the system, to show exactly where they fit into the whole element. So if somebody, for example, is very focused on software development, they may not understand quite how that software element is truly just a cog in the overall machine. Showing them a tree diagram like this is a good way to illustrate how their role plays into effect and is very critical, but also has to work in with others as well. What this simplistic view does not necessarily show is how subcomponents may potentially be integrated with multiple subsystems. So they may be having interactions or interdependencies all throughout that aren't necessarily shown in this diagram. That certainly can be shown, and some applications that's more applicable than others, but for this high level view and in many systems, this is a very good way to look at it and show that. System form follows function and then follows purpose. This is a very key element of systems engineering, maxim, that is not always understood or widely utilized. So for example, the purpose is why is the system being realized? So this is designed by the concept or the stakeholder requirements. That needs to be done first so that you can then lead into the function, what the system must do. So from there, you then get into form, which is how the system does it. So consider an example of cable television and remote controls. If people want to operate just the television, it comes with a single remote control that operates the television, turns it on and off, flips channels without any problem. However, if you want to use streaming services or DVRs or switch to a different movie type of projector, you will have to pick a different remote control or 2 or 3 different remote controls, and you have to hit a whole sequence of operations. You have to hit this button and that button and then get them all to work together. That is an example where they did not properly follow purpose, function, form. They start off with, here's the form, this is the remote control, and this is going to manage your system, and leaves it up to the end user to go and deal with the consequences. In this particular case, this has been technology changed as fast as possible, but this has been the case for many, many years and really shows no signs of changing or improving anytime soon. Had they had proper foresight and looked into this ahead of time, they would have been able to design this up front and it never would have been an issue. Conversely, now that it's integrated across all different components, that, if you will, of your television systems, it's very difficult to change after the fact. One example that comes from some of the readings is the purpose being manned flight versus aviary flight. So both of them have at a high level similar purpose of flight, but one with a human being and one with an aviary or bird. That's the purpose. The form then becomes either an airplane or a bird, and then the function then becomes all the different elements underneath. I won't go through this in great detail in here, but this is just a very simple view to explain how form or purpose needs to come first, then following by form, and then by function. The next maxim of system engineering is that a balanced system solution truly does require trade-offs. So these images here are a bit of a tongue-in-cheek view of what would happen if you had all different sub-elements completing their design without making trade-offs to other elements within the system. So for example, you might have one goal of trying to make as much power as possible. Then you might have another goal of trying to make it as easy to produce as possible, very manufacturable. You might have the goal to make it as durable as possible, or trying to make the flight last as long, or be the best ability to navigate while in flight. And the reality is, if you don't make any trade-offs in there, you will not find a truly optimal design system at the very end. Nobody wants to make this suboptimal system, and everybody wants to do the right thing, but people don't always look and see the whole, and that's why the systems engineer needs to be that devil on the shoulder. Sometimes those trade-offs make tough decisions necessary, and it's the responsibility of the systems engineer to both identify when those decisions need to be made and then make sure that those systems get followed through and then stay and don't get revisited. If a component is suboptimized, the overall system will never get to where you need to go. While nobody wants to make a specialist mad, the reality is if every specialist got everything they wanted all the time, you would never complete anything or get the optimal solution. It's important to realize while you're not trying to tick anybody off, you do need to explain here's why a trade-off needs to happen, and everybody needs to make trade-offs at some point in time in order to meet the requirements of the system. At the same time, while your subject matter experts may feel frustrated periodically, they should always understand that the compromises were made as the right thing for the entire system, and they were not done in a biased manner of one requirement over another. Even if you don't get yours particularly, even if you have to trade off something within your subcomponent, you should be able to walk away thinking, I know that I did the right thing for the overall system. All systems have risks that must be managed. This is another maxim that risk is present and the level of risk is always going to be there. Consider some typical risks encountered. Requirements do not adequately express the need. It's possible that you are in the requirements definition, and as thorough as you may be, you may still not get the requirements as robust as they could be. The system does not meet the technical goals or requirements. That could be because of requirements, or it could be because of delivery to said requirements. The technology will be immature or unavailable. Certain fields, especially in the computer or technology field, technology is changing very rapidly, and you may there may be a risk that your technology is immature or conversely is outdated by the time that you're done, and that may be a balance. Shrink wrap or commercial off-the-shelf components will not meet the need. Rather than custom build, if you go and purchase something right off the shelf exactly as is, it may not be tailored to your specific need. System development failure, loss of personnel, suppliers, those are potential risks of a system. Project cancellation, while nobody wants their project to be canceled, it's very possible that things could happen due to performance of the project or unrelated factors. Especially in large-scale projects, if external funding sources such as government or other large bureaucracies, those could change on a whim regardless of whether it's the right thing to do. System will fail its mission, similar to not meeting requirements, but system could fail altogether. Consumer injury obviously is a very critical one, and then environmental impact, not just for how the system will perform, but think of the disposability as well. The reality is all these risks will be present in some processes or some systems versus others, some more than others. But all of them should be reviewed and mitigated. If the risk exists and it's still the right thing to do, it's important to go and identify that and share that, because if the decision is made up front to accept a certain level of risk, then you can avoid delays down the road if those risks come up or people point out that there is this potential issue that could happen. Following a standard systems engineering process increases your probability of success. A standard process captures the organizational knowledge, allows for continual improvement, and helps to avoid repeating mistakes, and lets you leverage industry best practices such as external standards. Consistency is very key in today's business. The old saying is, variety is the spice of life, but the reality is that consistency is what pays the bills. And that's true in systems engineering. All that said, you do need to be adaptable. You need to make sure that your standards are adapted and tailored due to either changing business conditions or lessons learned. Not every process will apply universally, and reliance on process over progress will not deliver a system. Those are two truths that you have to look and say, while standardization is important and focusing on the process is key, you cannot lose your ability to be adaptable and to be pragmatic in the light of new information. This is the systems engineering V model that's viewed in the Blanchard and Fabricki text. On the left, you start with requirements. You define your system requirements and then proceed down to the bottom of the V by allocating functions to subsystems and designing your detail of components. This is your project or system definition aspect. From there, once you get to the bottom of the V, you start to go back up the right and verify the components and subsystems all the way up until your system is completely operational. This certainly will need to be adapted and modified, but this is a very true maxim in systems engineering. And while some cases this may be a little bit lopsided, the V may have more of one side than the other, it's a good fundamental concept that should be understood. So, in summation, there are 7 maxims of system engineering. They focus on the whole. Every system has a life cycle. Systems have boundaries, interfaces, and hierarchies. Systems form, function, and then purpose. So purpose first, then function, then form. A balanced system solution requires trade-offs. All systems have risk. Risk will be present and should be managed. And then following a systems engineering process increases your likelihood of success.